So last time we talked about the kinetic molecular theory of gases. Today we're going to get into the nature of gases. So what characteristics do gases have? The first characteristic gases have is called expansion. So expansion basically means to take the space up. They take the shape and completely fill the container they are enclosed in. That's because they have no definite volume or shape. Gas particles like to be very far spread apart. So the more room you give them, the more spread out they're going to be, if possible, just like the video shows you. The density of gases is very, very low due to how far apart the particles are. So if you remember back to chemistry 1, density is mass over volume. Obviously the mass is mass. Doesn't matter the container it's in, but the volume could change. The bigger the volume, the bigger the bottom number, the smaller the overall density will be. So because if a gas can spread apart, it will, your density of gases is very low. Some people like to say they're very light and airy. Don't like to use that word because that assumes weight, which density is not. But density is a measurement of how tightly packed together particles are. Gases are very spread out, therefore they have a very low density. Gases are also fluids. We think of liquids being fluid and we say liquids can flow, but gases also can. To flow just means that the particles can easily move past each other because there are weak or limited attractive forces. So technically, gases are actually more fluid and have more of an ability to flow than liquids do because they don't have a lot of attractive forces between the particles. So yes, liquids can flow, but so can gases. The next characteristic of gases or nature of gases is compressibility. So we talked about how gas particles do like to be very far apart. However, you can crowd them close together, but they don't like it. So in order to keep them close together, you have to increase the pressure. So think about, I'm going to use a solid, but it's because it's easy for you to think of. You take a handful of snow, and you have an overflowing handful of snow, and you take your other hand and you actually pack it together. You just caused those particles to get closer together because you are applying pressure. And when you let go, you now have a ball of snow, whereas before it was just an unidentified shape. So it's the same thing with gases. If you do apply pressure, they will crowd closer together, except high pressure is not what they like to be under. They're irritated, they're agitated. So think about oxygen tanks, okay, or aerosol containers. You have gaseous particles that are very close to each other because they're pressurized. What happens if you puncture them? The gases rush out. Okay, so that's why you have to be careful when you have containers with pressurized gas because they're not happy. So if you give them a chance to move apart, they're going to take it immediately, which brings us to effusion. So effusion is the process by which gases that are under high particles, if given the chance, will escape through small openings. So if you look at the video at the start, they're all closed, but as soon as you open, they start to escape. So that's why if you puncture a pressurized container of gas, it pops, it explodes, if you will, because all of those particles are rushing out because they want to be spread out. They do not like to be close to each other. When you're talking about effusion, if you do have a mixture of gas particles, these smaller and lighter particles will effuse faster. So it's like thinking about a crowded hallway. The smaller people can kind of squeeze through faster than the larger people. Okay, diffusion. Diffusion is when two or more gases mix together randomly. Gas particles are always in that random rapid motion, so they're going to mix together without being stirred. Two liquids, you kind of have to stir to mix them together, not gases. So the rate of diffusion, or how quickly gases will diffuse, depends on three things: the actual gas particle speed, the particle size, and the attractive forces present. So when we think about diffusion, think about spraying perfume, okay, or cologne. That is liquid that turns into an aerosol, which is gaseous. If you spray something on one side of a room, eventually the people on the other side will smell it. That's simply because those gaseous particles are mixing with the air. That's what happens. That's diffusion. I'm going to get a little real with you and say this is why, as a scientist, I understand the point of wearing a mask with COVID. Completely understand and support it. However, it is confusing to me as a scientist to put a mask on to enter a restaurant and then sit down at a table and take off that mask. Because as I'm sitting at that table, the particles that are exiting my mouth or anyone else's mouth are mixing with the air in that restaurant, going into the air vents and spewing back out. So I completely support mask wearing. However, putting a mask on to only take it off in the same location, diffusion of gases, people. I just want to have a mask that says that, diffusion of gases. But anyway, off my pedestal. Okay, and the last thing I want to talk about is a real gas. So we talked about ideal gases, which we know don't exist. The most ideal we can get is the noble gases, but they're also unique because they don't react with anything. So a real gas is basically just the opposite of ideal. It does not completely follow all the assumptions of the kinetic molecular theory to a T, and therefore they don't behave ideally. There's two major differences between ideal gases and real gases. Particles are closer together than we like to imagine. Ideally, we like to say they're very, 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 very spread out. Unfortunately, they're not that spread out. They're still spread out, they're not liquids, but they're closer than we like to think. And because of that, or I should say, they are closer together because there indeed are some attractive forces that are working against each other and attracting and repelling. The reason we say that the noble gases are ideal is because they don't want to attract anybody, because they do have that full outer shell valence electrons. So yes, they are pretty ideal. But most gases that we actually talk about, because we don't use the noble gases in compounds and reactions because they don't react, they don't bond, there are some attractive forces. Therefore, the particles are closer together than we like to imagine. So that was the second part of chapter 10. Next time we'll get into some math, and the rest of the chapter will pretty much be math.